Hello, our research is the learning search space-specific heuristics using neural network. I'm Liu Yu. This work was done with Kuroiwa and Alex Fukunaga. Heuristic functions have a significant impact on search-based planning performance, and the performance is domain dependent, and it's not easy to design new effective heuristic functions for new domains. So our goals are learn instance-specific heuristics, train a reasonably good low-cost heuristic, and fast training data generation and training. We hope that the total cost of learning and search could be competitive with search using standard heuristics such as FF. One previous research is the learning heuristic based on forward search. The major framework has 3 steps. 1. Training sample generation. For PDDL problem instance, I perform random walks from start state to generate training states S. For each small s and S, search from small s to find distance. The search is a standard heuristic search guided by an existing heuristic such as FF. The training process is trained just with the state and distance estimate as to get the model, and use the model for search. The learned HNN is an instance-specific heuristic for I, so solves I many times during training sample generation, so not particular setting when the task is to solve I once. And it also relies on teacher during training data generation. Next is a learning method based on backward search, LHCFP. A similar framework, but for PDDL problem instance I, the guess go state G and perform random walks from G to generate many state distance estimate pairs as training data. So the learning HNN is an instance-specific heuristic for I as well. It uses its own rows, subpath state vectors, and to learn from scratch with no teacher. Overall performance was comparable to blind search, but we can find that learning useful instance-specific heuristic from scratch is not easy. In obtaining training samples using backward search, first you have to find a goal state, usually guessed from the goal conditions, and go backward to find each state and record the steps as the distance estimated. There could be some issues. First, guessing or inferring a correct goal state from goal conditions is not trivial. And operations for backward search, if we just use forward operations, it could be insufficient. Also, if just use random walk, it can lead to inaccurate distance estimate. So we propose single instance network generation. The overall approach is based on HFCFP. The major differences are as follows. The previous one used sus vector as state representation, while we use strips, boolean 1 as vectors, as well as sus plus. The previous one used guess the goal state and original forward operators only for backward search space. We use 2 versions. One is guess the goal state and derive the inverse operators, and another one is regression search space. For backward search strategy, the previous one used random walk, while we use depth-first search. And also, we use relative loss function for neural network training, where the previous one used MSE loss function. In the case of explicit search space, because we guess the goal state based on goal conditions, and also we use derived inverse operators, so it might result in many spurious states in training data. But as a result, it turns out it also works with those states. So it's not necessarily bad, maybe just like generated data in GANs. In regression methods, the representation of partial states use the additional undefined value and corrected backward search so that there is no superior states. But regression space is not the same as forward search space. And also regression branching factors sometimes very large compared to explicit for backward search space. So the performance depends on domains. For backward search strategy, the previous research used random work, but it would cause to inaccurate distances due to cycles. And cycles could be avoided by hash table, but what to do if cycle detected? The reasonable way would be restart work when cycle detected. But the result will be a long path hard to be sampled if there are many cycles. So we use depth-first search. It allows sampling for a longer path than random work. Also, the drawback will be some overhead of backtracking. For neural network architecture, we try to use full connected neural networks with simple structure to run fast. Typically one hidden layer with 16 nodes or 4 hidden layers with 16 40 nodes in each hidden layer. And we also use Microsoft ONNX runtime on one CPU cores to make it run faster. Basically, the simple architecture causes faster evaluation. You can find in some domains we can perform the speed just between HFF and HLM. Also, actually, it's much faster than HFF. For loss function, we use relative error to reduce the effect of inaccurate samples with large distance training. Here's the configurations we used it for the experiment. Our last one saying L uses subplus state vector and random work and no inverse action operators. It was used as a comparison configuration, which is very close to the previous research. For evaluation of instance-specific learning on IPC benchmark results, we compare learning from scratch on each instances versus standard heuristics in 13 minutes per instance time limit, which include training data generation, training, and search time. We can find that this constraint is quite strict for a learning process because you include all the process in the time. And the same performs much better than the previous method, and it consistently be better than a blind search. It also outperforms HFI on 5 domains. We also get evaluation on shared search spaces. Here, heuristics is reused among many instances sharing the same search space, so the learning cost can be amortized. As a result, you can find in all the 4 domains in the experiment, HNN get the best coverage rate, and for node expansion in the domain of 24 puzzle and pancake, HNN is best. And HNN also gave the best runtime in 24 puzzle, 35 puzzle, and pancake. And the result was given under relatively short learning time and 1,000 seconds for all domains. Also, the search time competitive with HFF, HLM on all 4 domains. Why does it work? We compare the exact distance from the goal state and the heuristic value error. You can find the red one, HNN, close to the goal. Training data is quite accurate and promising. But from the goal, the training data become less accurate but still useful. Here's a comparison with forward search-based training data generation. Please be noticed these are new results, not in the paper. In the forward search-based training data generation method, for each 1C task, there are 200 instances derived by generating star states using random walk from original star state. And the teacher heuristic was launched to find the result to get the training data. So for saying, we tuned hyperparameters for 30 to 90 minutes in each domain. For each instance, Sing learns instance-specific heuristic from scratch. And for PDDL search results, they're from their paper. And then learns one heuristic from each domain, using much more time for training data generation than Sing. So you can find the result is somewhat complementary. For example, in coverage rate or node expansion, Sing performs better on domains such as blocks and puzzle, transport, and visitor. And also, Sing has much faster node expansion rate due to simple NN architecture. From the ablation study, we can also find comparing to the basic configuration, the configurations with no backwards search space methods or with random walk sampling search or with plus state representation or with MSE loss function, they all get worse performance. Here's the conclusion. We propose the same learning instance-specific heuristics by generating training data using backward search. It is based on HCFCP, but we have significant modifications on derived inverse operators, regression, state vector representation, and backward search strategy. We significantly improved the performance. Also, we get the performance competitive with HFF and HLM on shared search space settings when learning codes can be amortized across instances. Such performance is compatible to Fukunaga 2020 method, with much faster learning time. Very simple techniques can be combined to obtain surprisingly good overall performance, and in some cases complementary to well-known heuristics. Above all, we use no teacher heuristic, no feature engineering. Thank you.